Okay, everyone, I think we're going to get started. I think the Zoom should be working. So today it's my pleasure to introduce Professor Nathalie de Leon from Princeton. So her group's actually in electrical and computer engineering, but her group focuses on building quantum technologies from basically sensors, networks, with solid-state defects, especially in diamond, and also some more recent work working on materials for superconducting qubits, which is quite exciting. For this work, she's received a various amount of nice awards, including from the Air Force, a Sloan Research Fellowship, NSF Career Award, a DARPA Young Faculty Award, basically all the Young Faculty Awards. And she's also the Materials Thrust Leader for the Co-Design Center of Quantum Advantage, which I'd love to know more about, maybe during the lunch session. So we're really fortunate to have her here today to give a seminar in person. Lunch will be served afterwards, which is where you'll have an opportunity to speak with Nathalie a little bit more. And with that, please join me in welcoming Nathalie to give a seminar, and take it away.
I assume this is the right place to stand?
Yes.
Okay. Thanks for the introduction and for the invitation to come speak. It's nice to finally be traveling again after a couple of years. So because I'm finally traveling again after a couple of years, I think the seminar runs long. I will try to go as fast as possible, but don't be shy about asking questions in the middle of it, because I decided that it's good to show new stuff. So there's a lot of kind of preliminary data and hot news in the seminar. Okay, so broadly speaking, my group works on quantum technologies, as Chris mentioned. We're basically split into three right now in my group. So about a third of my group works on quantum sensing, particularly nanoscale quantum sensing with these pointy effects in diamond. A third of my group works on quantum networks, where we're really focused on finding new solid-state defects and then integrating them into nanophotonic devices. And then about a third of my group, this is a new effort since about 2020, on working on new material systems for quantum computing, particularly for superconducting qubits. So one of the nice things about being at this stage in your career is that you actually can't talk about absolutely everything that you work on. So won't fit in one seminar. So unfortunately, I won't have time to talk about this topic today. But I know that there's a lot of interest in that around here. So feel free to come find me and chat later about kind of new results. Okay, so on the quantum sensing side, what we're mostly focused on is the nitrogen vacancy center in diamond. This is a color center in diamond that you get by taking a diamond lattice, taking out 2 carbon atoms, and then putting 1 nitrogen back in, so that you have the substitutional defect next to this vacancy in the lattice. And the reason that this is a really interesting defect is that if you look at the electronic states associated with the NV center relative to the conduction and valence band edges for diamond, you really get this mid-gap state. And then diamond has a large enough band gap that you have enough headroom that you can even have orbital excited states that are still very, very deep mid-gap states. So to first order, you can really think of these as molecular orbitals. Like, you don't really have to consider the extended lattice at all. And it turns out that the NV center has, it's a spin 1 defect that has extremely long coherence times, even at room temperature. So the coherence times are really limited by a spin lattice relaxation that's about 7 milliseconds. And this is really unprecedented. Like, there's essentially nothing else in the solid state that has such long spin coherence times, including other atomic defects. And there's also a very convenient mechanism for optically manipulating and measuring the spin, basically just using a laser that is not very much more sophisticated than this green laser pointer. You can just shine light on the defect and spin polarize selectively into one of your spin sublevels. And there's also a mechanism for reading out the spin resonance optically. If you start in this ms equals 0 spin sublevel, I can just sort of scatter photons and cycle back and forth. But if I start in one of these other spin sublevels, there's a spin-dependent inter-system crossing to a dark state. So just by counting the total number of photons I get back, you can read out the spin sublevel. So you get this nice sort of ODMR dip, and you can do things like read off the local magnetic field by looking for Zeeman splitting, and do coherent manipulations on the single electron spin. So the general picture here is you take sort of, almost 100 years of magnetic resonance development, and then maybe like 40 years of single molecule microscopy, and you combine them so that you can do all this single spin manipulation. And basically, because of these properties, there's now dozens of groups around the world that are all really focused on this single color center in diamond. This is now sort of mature in a field that I should probably stop showing this list because it's more of a political liability than anything else, but it's really a very large number of groups that are focused on this color center. So one of the reasons that people are really excited about NV centers in diamond is because you can use them as nanoscale sensors. So because the defect itself is really a true point defect, then you can imagine doing things like looking at dipolar coupling between this electron spin and other things that are in the lattice. So for example, if I just plot here dipolar coupling strength as a function of distance, you can see that these contours change very, very rapidly over extremely short length scales. So one way to think of this is it's a lot like magnetic resonance imaging, except you have the largest possible magnetic field gradient because you're really starting with a point sensor. So there's been a lot of activity in trying to deploy NV centers as sensors, for example, by decorating the diamond surface with molecules and trying to do nanoscale NMR. There's even been some developments over the last half decade where there are new pulse sequences where you can even push this all the way down to being able to do chemical shift level resolution NMR. And then there's quite a robust community using NV centers to try to study condensed matter systems and materials, with this beautiful example from Patrick Malatinsky's group from a couple of years ago, where they uncovered sort of new mechanisms for magnetism and chromium triiodide, which is one of these 2D materials. So just to show you sort of the power of the sensor, this is an example from Tim Tamenyau's group at Delft from a few years ago, where they're looking at a single NV center sort of deep in the diamond, and then they do these kind of NMR pulse sequences to look at individual carbon-13 nuclei in the diamond. And they're able to really map out the positions of, I don't remember how many it is, but I think it's actually at the title of their Nature paper. It's like 27 carbon-13 nuclei. And you can see that they really have these positions all the way down to this deep sub-angstrom scale. So this is really incredible. If you could do this for something that is a little bit more interesting than something that's in the carbon-13 nuclei in diamond, this would be an incredibly powerful tool. Okay, so this is very beautiful work. But now, what we really want to do is now take this NV center and do really similar things, but for arbitrary sensing targets. So for example, if I take, this is a physicist version of a protein, a little blob of nuclei sitting on the surface, and I want to try to sense it. Now, I need to get extremely close to this protein to get very high spatial resolution. That part is obvious, but also sensitivity is going to scale as something like distance cubed or distance to the sixth, depending on exactly what you're doing. So you really want to get extremely close to this thing. But now getting really close to this thing also means that I have to get really close to the diamond surface. And while mankind is quite good at making extremely high purity diamond now, we're really bad at, I would say, surfaces in general, and diamond surfaces in particular, because diamond is a very hard material. So it's hard and inert. So basically preparing surfaces in a way that gives you low noise is an outstanding challenge. And you can sort of think of this as the NV center is extremely sensitive, but it's going to see both the sensing target and this big background noise path. So one of the ways that we know this is that you can just look at individual NV centers and look at their coherence time as a function of depth. And I told you earlier that you can get to coherence times of many milliseconds at room temperature. And that's true if you're around 100 nanometers or a few hundred nanometers away from the diamond surface. But once you get very close, we see this horrible sort of 1/4 roughly power law scaling. Such that when you're within, let's say, 5 nanometers of the surface, people see sub-microsecond coherence times. And this is, each of these colors are different samples that are prepared in slightly different ways. So we basically see this sort of no matter what. And there are many other groups who have also done very similar measurements and seen roughly the same scales. Okay, so what we'd like to do is now try to mitigate this surface noise. And one of the challenges is that the NV center is a very sensitive probe, but in some sense it's very non-selective. It's basically, it's going to tell you, I have a long coherence time or I have a short coherence time. It doesn't really give you any clues about the microscopic mechanisms of this noise. There exist ways to study the surface directly, like you can do surface-sensitive spectroscopy, but in general, these techniques are quite challenging, and a priori, maybe more fundamentally, they probe much larger areas than what the NV Center is looking at, and they have very low sensitivity. So it's not actually obvious right off the bat that you're going to learn information that's relevant for the surface noise that dominates NV decoherence. And there's a number of other technical problems associated with, working with diamonds specifically. So about 6 years ago, my group embarked on a pretty broad project of trying to do, well, the dumb experimentalist thing, which is to just try every surface spectroscopy technique and see, if we look at this diamond surface in gory detail, can we find anything that is correlated with, the quantum measurements that we can make on single NV centers. So you get this sort of alphabet soup of a large number of electron-based techniques, X-ray-based techniques, scanning techniques, and we sort of zeroed in on X-ray photoelectron spectroscopy, ultraviolet photoelectron spectroscopy, and near-edge X-ray absorption fine structure as being sort of the key tools that actually ended up being helpful. And then we can do something a little bit more sophisticated than just asking the NV Center if it got like happier or sadder, and take advantage of some of these pulse sequences to try to do spectroscopy of the noise bath by driving the NV Center in different ways. Okay, so one of the things that we figured out almost instantly on this project is that a lot of the community talks about how you need oxygen terminated surfaces to stabilize NV centers, but when they say oxygen terminated, those can be very, very different types of surfaces. And in particular, if you just have two slightly different starting morphologies and then put them through the exact same processing, you can get these runaway surface roughening processes that lead to extremely different final surface morphologies. And this is because a lot of processing in diamond is very hysteretic. So depending on where you started, you end up in very different places. And what we can see in the X-ray spectroscopy are drastic consequences to the electronic structure just from this difference in surface morphology. So you can think of this as X-ray absorption that's probing the density of unoccupied states. This sharp peak here is the exciton peak in diamond. So everything to the right should be there. It's part of the band structure of diamond. Everything to the left should not be there and is basically just defect states. And you can see that this rough surface has this big tail of defects, whereas the smooth surface just has a couple of small peaks that are associated with the surface termination. So these are really natural candidates for this magnetic noise because now I just have a large number of electronic traps that can host, charges transiently that then lead to this noise. Okay, so to spare you the really extremely long story about all of the different failure modes that we learned, basically the end result of that is that we now have this multi-stage process for being able to create very pristine oxygen terminated surfaces. So we start with very smooth, low subsurface damage diamond that's polished in a particular way. And we have to do reactive ion etching to remove the polish damage. That leaves behind some etch damage, which we then have to etch away with a different etch. That leaves behind its own etch damage, which we then have to anneal away with high temperature annealing. And then we have a final oxygen annealing step to create our last surface. And then the key thing is that you have to do this in a way that you don't introduce these surface morphology problems. So you have to really do contamination-free processing at every single step. And we're now able to get these oxygen-terminated surfaces with RMS roughnesses of below 100 picometers over a micron, and then something like 300 picometers over 5 microns. Under these surfaces, we get much, much better coherence times. So these are all the data points that I showed you earlier. And then these dark green points are sort of a typical best surface where we're able to get extended coherence times by about a factor of 10. And actually, it turns out you can dynamically decouple to a couple hundred microseconds, actually, even at these depths. So now if you don't want to know anything else, you can fall asleep for the next 5 minutes because this is sort of the takeaway message. But what we can do to try to understand what the source of noise is zoom in on kind of these final two surfaces before and after this last oxygen annealing step. And we can look at comparisons of individual NV centers sort of before and after this step. So if we just do, say, a Han echo sequence to look at the spin coherence time, this is now one NV center where we can find an individual NV, do this last oxygen annealing, and go back to it. And we can see that the coherence time is extended by about a little bit over a factor of 2. And then if we do dynamical decoupling to try to extend the coherence, you can see that before this oxygen annealing, you actually stop winning from dynamical decoupling, so it saturates. And that's the real killer, actually, the fact that you have this really broadband noise that you can't even decouple away from. Whereas after this oxygen annealing, you still get scaling all the way out at 40 to 100 pulses. We can also take advantage of the fact that the NV center is a spin 1 ground state and do relaxation spectroscopy. For first order, you can sort of think of this as if I look at a single quantum transition where I go from ms equals 0 to either -1 or +1, you can drive that with magnetic fields, whereas changing the sublevel by 2 is not allowed by magnetic fields. So this is sort of a probe of the relative electric field noise contribution versus the magnetic field noise contribution. And what we can see is that it's predominantly a magnetic field noise change because you get this big change in the single quantum T1, but a smaller change in the double quantum T1. And we can, work hard to try to put all of these things together on one footing to create one nicely parametrized plot where we look at the electric field noise with its 1/f scaling compared to the magnetic field noise, and we see that the magnetic field noise is really dominant by about 2 orders of magnitude. Okay, so those are the NV measurements, and then we can also do this surface spectroscopy to see what changed in the surface spectroscopy. And again, we can look at this sort of near-edge X-ray absorption technique. And, I would say that these are sort of broadly similar. I think surface spectroscopists get really annoyed when I say it that way because they can see a lot of other things in this data. But, there's like a peak here, and there's some like broad thingy over here. So there's not like a clean story that you can tell that you have one thing has ketone and the other one has alcohol or anything like that. But there is a very clear difference between these spectra, which is that after oxygen annealing, you get this big polarization dependence, whereas before oxygen annealing, it's all just washed out. So the picture here is that you have broadly similar chemical structure of the surface, but the big difference is that you have a lot of surface disorder that gets cleaned up in this last step. That gives rise to well-ordered atomic bonds, and that's why you're able to recover this polarization dependence. Okay, so that's this is now like a little bit of an old story. So I just wanted to impress upon you that we're able to understand the diamond surfaces, eliminate sources of noise, and then use that as a basis to get very, very nice shallow NV centers. So now what we want to do is actually try to use them for stuff. One of the things, so this is now like very preliminary data stuff that we're just writing up now. But one of the things that we've been really excited about is trying to develop these shallow NV centers as a tool for a different type of magnetometry than what people have been working on previously. So I put traditional here in quotes because obviously there's nothing about using a single atomic defect in diamond for sensing is traditional. But what a lot of other groups have been working on is basically doing ODMR at this NV center, collecting photons and trying to read out the magnetic resonance and using that to just measure the magnetic field. Okay, so you sort of pick a single place, you measure the magnetic field, and then you use something like noise spectroscopy or drive it with different pulse sequences to learn something about the system that you're looking at. So this is some nice work out of Misha Lukin's group from a couple of years ago, where they, for example, put a graphene sheet on top of the diamond, and then they're looking at transport using the NV center as a local probe, and they were able to see some nice electron phonon coupling physics. And this is essentially what everyone is doing, whether you're doing scanning or just making kind of sandwiches of things. You're basically just measuring the magnetic field for the magnetic field noise. So the question that we asked was, instead of just looking at a single NV center and then looking at the magnetic field, can I learn anything new if I just look at correlations, temporal correlations in the outcomes of multiple NV centers? So one way to think about this, and I realize this is a really ugly cartoon, I apologize, is that if you're looking at this transport problem, right, where I have electrons that are transiting past 2 NV centers, then if you just did this traditional magnetometry and I just asked this NV center, what do you see? Then it would just report back, I see Johnson noise, right? Like I see some white noise bath. And then if I ask this guy, what do you see? Then that NV center would also say, I see Johnson noise. And you don't really learn very much other than they're both looking at transport through some material. But if you put these NV centers close enough that they were within the mean free path of electrons that are transiting in this thing, and you looked at correlations in their outcomes instead of just asking, what do you see in magnetic field, then you should see some signature of the fact that you have single electrons that are transiting past both of them, right? Because as an electron goes past both of them, you should see a correlation in the noise path. So that's the general picture. Okay, so now, like, how do you parameterize this? So the person who's been leading this project is Jared Rothme, who's a postdoc in my group, and we also started collaborating with Shimon Kolkowitz at University of Wisconsin Madison. So the general picture is you have two NV centers, and each of them sees some global noise that you're trying to learn about, right? And that's where you're trying to learn through these correlations. And then each NV center is also going to have its own local noise bath that you don't have a lot of control over. This could be carbon-13 nuclei or other defects in the lattice. And now what I'm going to do is a pulse sequence where I put the NV center on the equator of the Bloch sphere, I let it accumulate phase, and then I tip it to make this pancake that's along this axis, right? So, I come down, things spread out, and then I flip it like this. Now, normally this is a terrible thing to do because everything sort of averages out and you would get zero signal. But here, now if I ask, can I see correlations between these two things? I suddenly recover all of this phase information. So that's the general picture. But now you actually need to figure out how to parameterize this in a way that makes sense so that you can write down, a pulse sequence that actually works. So this was our COVID theory project. So the parameterization is, you have some phase distribution between your two NV centers. So that's this, this is just like Bayesian statistics, right? So you have this phase distribution. On top of that, you have some quantum projection noise. So I do my final measurement, and you don't get infinite information for free. So you have some quantum projection noise added onto it. And then I also have some readout noise that I can't read out my states perfectly. So, here's the general idea is I'm, driving these two NV centers. I get this phase distribution, and then I ask, do they correlate with each other? So what you can kind of immediately see is that, well, actually, I guess it's over here. Is that, the real problem is that you need very, very high readout fidelity. So if you just collect photons from these NV centers, on average, you tend to get 0 photons. So if I just take a time trace, I think this is real data, actually. If I just take a time trace from two NV centers, then my probability of getting a coincidence between two NV centers is essentially 0. So you just have no shot at ever being able to measure this. So the key thing, from this perspective, is that what I need to be able to do is cleanly separate these distributions and decrease this readout noise in order to get any shot at measuring correlations. So with the traditional spin readout, this is very, very difficult to do. But one of the things that I worked on right before leaving Nisha's group, together with Brendan Shields, was this mechanism for improving your readout fidelity using spin to charge conversion. So it turns out that there are ways to selectively ionize the NV center to convert the spin state into a charge state. And then it's actually very easy to read out the charge state with single shot fidelity. That's very funny that you can see people on the screen. So at the time, we were very excited about this, and then immediately not excited about it, because you can see that this readout window here is something like 2 milliseconds. So this normally doesn't help you at all, because if you're doing normal magnetometry, taking this overhead of 2 milliseconds is really catastrophic, because all that you care about is how small of a magnetic field can I measure with some integration time. So if I add this 2 milliseconds of overhead per shot, then you're never increasing your sensitivity. So not useful for traditional magnetometry, but extremely, extremely useful for this covariance sensing. So now we can just parameterize everything as sort of like a minimum magnetic field to achieve a signal to noise ratio of 1 for some total experiment time. And your conventional readout gives you this line here. So you can see that, in order to basically measure, let's say, a nanotesla, you're talking about something like 10 to the 6 seconds. So that's not a fun experiment. Nobody wants to do that. And with the spin to charge conversion, you can get this all the way down to something like 10 to the 4 or even 10 to the 3 seconds. So this is now in sort of, not fun territory, but like reasonable for a PhD. So people can kind of do this experiment. And then you can just write down what the optimal would be if you just had a sigma, if you had a readout noise of 1. Okay, so these are now some numerics. So if you have an NV center that has sort of this coherence decay, and then you ask, if I have two NV centers that have this coherence decay, what do the correlations look like? Then, by quantum projection noise, you're sort of stuck at a Pearson correlation of a half. And then, kind of intriguingly, you see these dips wherever their local noise takes over. So it's sort of this funny way of actually measuring these carbon-13 nuclei that you see the correlations disappear. And then you can do things like spectral decomposition, where you can also look at the spectrum of these correlations. Okay, so that's as far as we got until like January or February, and then we went to actually build this experiment. So in order to do this as a first pass, we just built a 2-channel galvo, where we have a two galvo microscope, where we just have 2 galvos that are staring at the same sample, and then we can independently control the excitation and readout. And it turns out that when you build an experimental setup to measure correlations, you sure see a lot of correlations. So there's a lot of trivial correlations that are things like the whole table moving up and down, and your HVAC control kind of cycling on and off. And the way that you can tell that there are trivial correlations is that you can just save all of the data and then do a registry shift, where if you just move them by 1 point, all your correlations should disappear. But instead, what we could see was this periodic signal, which means that there's just some kind of low frequency noise that's imprinted on all of this. So after a lot of pain and experimental hunting and all of that, we can now sort of beat down all of these technical correlations so that we can get down to a background correlation rate that's something like 0.0004 or something. Okay, so now armed with all of that sort of technical pain, we can do some correlated driving. So here's 2 NV centers in this confocal microscope. We can just drive them both. So this is trivial. This has nothing to do with noise. This is just intentionally driving both NV centers. And then you can see that you get these sort of positive correlations that depend on my pulse length, the way that you should with a Rabi oscillation. And then we can look for anti-correlations by shifting this data register by 1. And then the important thing about this plot is that this 0.006 we understand completely. So it just comes from our direct measurements of the quantum projection noise and the readout noise. So this is quantitatively accounted for. Okay, and then now we can do this experiment that we did in numerics, where we just intentionally inject white noise into an antenna and then try and measure these correlations. And we indeed see very high correlations. And then we see that they disappear over the carbon-13 signal, and that it matches really well to just doing kind of traditional NMR of the carbon-13, where this signal appears. And importantly, when we do the single point shift where we expect the correlations to disappear, they really, really disappear. So we're sure that we're measuring a genuine thing. Okay. And then finally, we can also just inject sort of a narrowband tone at 2 megahertz, and then intentionally randomize the phase, and then see whether or not we can see that in correlation for both NV centers. And we indeed see this very beautiful correlation around where we expect to see a 2 megahertz signal. And then we can just do a really simple thing, which is prepare the NV centers on opposite sides of the Bloch sphere and look for anti-correlations. And we see this beautiful anti-correlation. And the interesting thing is we actually figured out that our signal generator was supposed to have no phase memory when you programmed it in a certain way, and it totally had phase memory. And you can see there are all these like kind of funky little patterns. And this is something that you would have no shot at ever measuring with traditional magnetometry, because you just see that you saw a 2 megahertz signal. But we're now able to see this like funny phase memory over extremely long time scales compared to the coherence time of the NV center. Okay, so that's where we are right now. I'll just say I think this is a very powerful tool. And we're currently looking at a large number of possible outstanding problems in condensed matter. And I've been trying to talk about this as much as humanly possible, because I think there's a lot of problems out there that people have been trying to get at with things like neutron scattering and STM, where you just don't have any shot at all of measuring spatiotemporal dynamics. So now we have a completely new probe where you might be able to learn new physics. Okay, so I'm going to totally change gears. So if there are questions about what I've talked about so far, maybe I should pause for a second. A lot of this work was actually Ahmed's project during QRIP, and It's like the best undergrad ever. Yeah, go ahead.
I have lots of questions. I'm just curious, is this finished version working?
Yes, that's how we're able to do
Okay.
this. So if you
What's
have a
the
readout
fidelity
noise,
that you measure?
we have single shot readout.
At room temperature. That's great.
Sure, yeah, I don't know exactly what it's probably 0.95 or something. I'm not going to quote a number because I don't remember exactly what our threshold is.
Awesome.
Yeah, if you did traditional readout, no hope of measuring this. That's many PhDs. No one's willing to integrate for that long. Okay, so now the other kind of big project in trying to deploy these sensors is to take a serious look at, what would it take to try to use these NV sensors as a tool for biophysics? Okay, so this has taken us down a general path of figuring out how to do new types of diamond surface functionalization, and this is led by Leela Rogers, who's a senior grad student in my group. Okay, so what would you need if I wanted to do, this is now like a slightly more sophisticated version of the protein, right? Like it's an actual picture. I think this is ubiquitin or something. So if I have this NV center and I want to do this nanoscale NMR experiment, then now what do I need? So I need highly coherent shallow NV centers, and I've told you an entire story about how to do that. You need to be able to immobilize this protein at the surface somehow, because it needs to not diffuse away while you're trying to measure it. You also need to figure out a way to attach it such that it retains its biological functionality, right? You need to be measuring actual stuff and not just junk. And then there's, I think, actually a big kind of theoretical frontier on figuring out how to make these measurements fast so that you can actually measure dynamics. Okay, so what I'll be talking about in this part is mostly sort of these two pieces, which is how do you immobilize these targets on the surface and how do you do it in a way that's still compatible with these highly coherent shallow NV centers. And this is all work done in collaboration with Rob Knowles' group in the chemistry department. Okay, so the challenge here is that single crystal diamond chemistry is very, very harsh. So diamond is inert, it has a very tight lattice. Diamonds are forever, whatever. and normally, if you just stick it in some solution, the solution is not going to do anything to the diamond at all. So the way that people have to functionalize diamond usually involves things like, high temperature thermal processing, sometimes even at high pressures, and plasma. And these things can be quite damaging, as we have painstakingly cataloged in the past. So, in general, it's hard to make this compatible with very coherent shallow NV centers, but more importantly, this really limits the scope of things that you can attach onto the surface. It's very difficult to imagine a protein surviving, something that glows. So there's been some interest in this lately, and there's been a nice sort of pair of papers that just came out this year. This was some work that we were involved in collaboration with Peter Maurer's group at Chicago, and it sort of came out together with a paper from Dominic Bucher's lab, where instead of functionalizing the diamond, maybe we can just ignore the diamond and put down a functionalization layer like ALD alumina, and then use all of the beautiful chemistry that people have developed in the biophysics community to functionalize alumina. Okay, and this is very nice, and it works quite well, but it comes at the cost of offsetting your NV center even further from the things that you're interested in, and we pay for distance as distance to the sixth. So this is actually a pretty big cost. And the other sort of challenge is that these alumina layers introduce their own noise. So all of this kind of careful work that we've done to make a really quiet environment gets a little bit degraded by this approach. So what we want to do is now try to just attach things directly. And the thing that Rob Knowles pointed out that was really intriguing is that there's been a real revolution in the last several years in diamondoid functionalization. I should probably take this moment to just apologize in advance for how much chemistry there's going to be in the next 5 slides. There's nothing that makes me feel less like a chemist than the fact that we call this the chemistry project in my group. But I'm very excited about this stuff. So I'll try, and then you can stop me if anything gets confusing. I only barely understand this organic chemistry stuff. Okay, so the general picture is these diamondoids are small molecules that look a lot like diamond, right? This is basically like the diamond lattice, but it has, a finite number of countable atoms, and then you can sort of tile these to make larger and larger molecules. In general, these are very hard to functionalize, and there's actually sort of an outstanding goal in the community for many decades because like Exxon and all of these people who crack hydrocarbons can just make buckets and buckets of this stuff. It's just a byproduct, but they couldn't figure out what to do with them because nobody could actually do any chemistry. So people would really love to be able to do something with them, and they were just handing money out to organic chemists to try to do this for many years. And the way that people cracked this field open was with this new class of catalysts called photoredox catalysts. This just got the Nobel Prize last year. Oh no, sorry, it did not get the Nobel Prize this year. Its inventor got the Nobel Prize for a different thing. But anyway, these are a class of catalysts where they have very different catalytic behavior if you just shine like blue light on them. So you just turn on blue LEDs and then you make totally different things. And there's a specific class of catalysts that perform what's called hydrogen atom transfer, where you have a CH bond and you have a catalyst that just plucks off this hydrogen and leaves behind a little radical in solution, and then you can basically trap that radical with other things that you intentionally put in. So the general scheme here was that we start with our oxygen terminated diamond, we convert it to hydrogen terminated diamond, we do this hydrogen atom transfer, and then we put something on the diamond surface. And the nice thing is this is all at room temperature with visible light. It's in very, very gentle conditions. Okay, so this was basically Rob Knowles' idea. He didn't think it would take that long, and I said, well, lots of people have been trying to functionalize diamond for like half a century, so I don't know why you think this will be so fast. But Rob is a genius, so it went really fast. So basically, one of the real challenges here is that we now need to be able to do reaction discovery, but on this single monolayer of atoms at the diamond surface. And the typical reaction discovery tools are things like chromatography, liquid phase NMR, mass fragmentation mass spec, infrared absorption, and none of these things have sufficient sensitivity to be able to look at this, one monolayer of atoms on top of an Avogadro's number of other atoms. So our approach instead was to intentionally functionalize with heteroatoms and then use X-ray photoelectron spectroscopy to screen. And the idea here is that you can do a lot with this screening, basically with these sort of rapid feedback tools in the lab, and then you can back it up with more detailed measurements using sort of detailed surface spectroscopy and going to a synchrotron to look at X-ray absorption. So here's an example of how this pipeline works. So this was a reaction where we were trying to put a nitrogen-containing group on the surface. Before the reaction, you see no nitrogen in XDS, and the AFM gives you this nice smooth surface with just these polish marks. And then after the reaction, you see this nitrogen peak. So yay, it looks like we have nitrogen. But then if you go to the AFM, you can see that there's just all this junk on the surface. So one thing that really helps you here is that if you have non-specific binding to the surface, the probability that it gives you a perfect monolayer that's totally conformal is essentially 0. So most things will actually show up if you just take a look. So then if we try to clean it to get it to a stage where it looks, clean, then you can see that this nitrogen peak goes away, and that means that this was a failed reaction. Okay, so after a lot of pain and iterating on things like that, we were then, able to find this hit where we discovered new fluorination chemistry. So we can do one of these hydrogen atom transfer reactions to put fluorine on the surface. You see a very clean fluorine peak. We can do basic hypothesis testing, like if I don't turn on this light to do the photocatalysis, we don't see this fluorine peak. And I see that this fluorine is very, very robust to many different things that I can throw at the surface, including boiling in perchloric, nitric, and sulfuric acid for an hour. So we really think this is covalently bound to the surface. The AFM looks clean, and we can even see this beautiful 2x1 reconstruction pattern in LEAD that shows that it's a very nice and well-ordered surface. Okay, so that's all very suggestive, but now we can go to a synchrotron source to again do near edge X-ray absorption fine structure spectroscopy, and we take advantage of this thing that I mentioned earlier, where we can look at the polarization dependence of the signal, and we see that if we look at the fluorine edge, you see this clean polarization dependence, which really indicates that the fluorine is covalently bound. All right, once we have that first hit, it turns out that this chemistry is very generalizable to many other functional groups. We can put sulfur-containing xanthates on the surface. We can put chlorine on the surface, and it's all very, very broad. The other thing that we discovered is a method for being able to attach amide groups to the surface, which are very helpful for functionalization. It was a little bit of an accident, and this is a mechanism that we were not expecting. But the kind of neat thing is that what we were able to do was come up with a proposed mechanism for putting this amide group on the surface. And then we could take that back to these diamondoid molecules and then verify that the chemistry worked using liquid NMR. And I will say something a little bit controversial, but I think is just correct, which is that I think this is the very first time anyone has ever done diamond chemistry and ported it over to diamondoids, which is how you know that this is genuine chemistry. And I think most people who are doing nanodiamond chemistry, it works on the nanodiamonds because the nanodiamonds have extremely defective surfaces. So when you try to port even nanodiamond chemistry to single crystal diamond, it tends to not work. And it definitely doesn't work when you try to do it on small molecules. So I think this is a really powerful pipeline for being able to discover new chemistries. I'm not going to say that this is how you should figure out new diamondoid chemistry, but I think we at least know what we're doing on single crystal diamond. Okay, and then this amide group, you can now do all the things that you learned about in freshman organic chemistry to try to attach things to that amide group. We can do hydrolysis to make an amine and then attach that to other things. And then we see that we have them covalently bound to the surface. Importantly, this chemistry is all compatible with making coherent shallow NV centers. So with NV centers that are within a few nanometers of the surface, we can see ODMR, we can drive them. And then if we make a plot of T2 versus depth, all of these different surface functionalizations give us a curve that is basically in line with our typical best. And then we can dynamically decouple, again, up to a couple hundred microseconds. Okay, so our ongoing work is to now try to sense something that we intentionally put on the surface with NMR. For example, this is just a proof of principle thing where we can intentionally put perfluorinated oil on the surface and we see this clean fluorine peak next to our hydrogen peak. So now what we're trying to do is put some big fluorine group and then do the same exact experiment. Okay, so just to conclude the NV work, we've demonstrated this method for making very coherent shallow NV centers. We're developing new quantum spectroscopy tools to try to study things using these NV centers. And then we have this ongoing project in the group to actually develop new types of surface chemistry to enable the single molecule NMR and try to develop the NV center as a biophysics platform. There's a lot of other work going on in my group that I didn't have time to talk about. I'll just mention it here in case anyone is interested to talk later, but we showed that by looking at the shape of the coherence decay in a very detailed way, we could uncover interesting information about the spin dynamics of defects at the surface. And this general technique of data analysis has now found a lot of broad application in many other quantum platforms. So I do really like this work, and we'll talk about it at length if anyone is interested. We're also doing some new types of surface chemistry by building, we built this tool in my lab over the last several years. It's an ultra high vacuum cryogenic confocal microscope, which I think is the first one of that combination of words in the world. And we have to solve a lot of technical things to be able to make this work, but we have high NA imaging and high Rabi frequency manipulation all in ultra high vacuum, so 10 to the minus 11 to 10 to the minus 10 torr. And then we've also been thinking a lot about how to manipulate itinerant carriers, basically, putting carriers in the conduction band or the valence band, and then looking at them get captured and moved around. Okay, so I'm going to really change gears now and talk about a very, very different physical system. So again, I'll just pause for a minute in case there are any questions about NV centers. There's going to be a lot of whiplash. Yeah.
I guess I was wondering, you have multiple NV centers and your correlations. If you have any ideas about using, say, interactions to improve your measurements, or if you could generically, have an NV center kind of be coherent in your sample and have some other defect that couples to the NV center and sense and maintain.
Yeah, no, it is a very interesting question. So there's this whole group of people who are working on quantum enhanced sensing, where you actually use entanglement, for example, to get better sensors. And it's a very interesting direction to go in and sort of combine with what we've shown. I just want to emphasize everything that I showed is just classical. So you can do a lot. You can do a lot with just classical correlations before you get to anything fancy. But yeah, it is an interesting direction in general to see if you can make entangled states with multiple NV centers and use that instead. Yeah.
Just so I understand the biophysics story. So you have this really precise thing which you'd like to put your molecule of interest or whatever close to, and then the whole diamondoid chemistry was to bond for now a test thing, but eventually the molecule of interest, or is it that you're kind of putting a receptor that then you would want the molecule of interest to, or how does that work?
Yeah, so right now it's all just like it's a toolkit for being able to put, so we haven't put a protein on there. But what we do have is an amide bond. So that's sort of a natural building block for sticking big bulky things on there.
Then you said that it was very rough, and then you had these like cleaning steps after, but the whatever this technique is resistant to all those cleaning steps. But then for an actual biomolecule, do you expect it to also be, after you bond it, you can clean it and
Yeah, sorry, I want to make sure I don't mix up the story too much. So the point of the cleaning was to prove that we formed a covalent bond. It's not necessarily that all this physisorption is like that big of a problem, but the question is like, do you know that you've done it in chemistry, right? And it's very hard. The alternative hypothesis is always non-specific binding. So you need to find some way of distinguishing between your putative reaction and non-specific binding.
got it.
I'll get on my soapbox for like half a minute and say that if you look at like the what people did in like single molecule FRET, for example, they had all those pieces figured out in the early 90s, and then it took them another decade or two to get to a point where they were actually learning things about biology. And a very large fraction of what they were doing at that time was figuring out how to functionalize glass, right? And then proving that the way that you functionalize glass didn't totally screw up your protein activity or whatever it is that you were trying to do. So I think that's roughly the stage that we're in now, right? We have all of these components and we have a lot of tools. And now someone actually needs to figure out how to do this kind of next stage of development so that you're actually looking at something that people find interesting. Okay, with my last 15 minutes. So this playbook that I told you about, where you do detailed quantum measurements and then correlate them with direct materials characterization and surface spectroscopy, that was something that I ran around talking about for several years. And then people would come up to me after seminars and conferences and say, like, I think our field also has problems with surfaces and interfaces. Can you just come and solve what's ailing quantum dots or trapped ions or whatever? And I was very resistant for a long time because I didn't want to just be some person who came in and solved materials problems. But then I got sort of nerd sniped into this problem. So it helps that Andrew Houck is right down the hall. So superconducting qubits, totally different system, are a very successful quantum bit, as many of you know. So all of the major industry efforts now are basically built on superconducting qubits, including this this beautiful work out of Google Quantum AI, where they're able to make these processors with dozens of qubits and then show that, for example, you can simulate random circuits much more efficiently than the most powerful supercomputers. And they've been doing some very nice physics with these things too. Okay, so this is a really great platform, but one of the kind of funny things in the field that nobody would talk about for several years is that if you made like a Moore's law type plot of superconducting qubit coherence over time, there was this enormous amount of progress from the late 90s to about 2010. And then the last time anyone set a record for a planar superconducting qubit was roughly 2012, when they hit about 100 microseconds. So everything above the line here is cheating. It's things like making a 3D cavity and then just looking at the lifetime in this microwave cavity. But there just been this total stagnation for almost 10 years in just improving the lifetime of superconducting qubits. So there are a few things that people know about these losses. The first is that the losses appear to be related to surfaces. If you just look at the bulk components, the bound should be something like 10 to the 9 or even 10 to the 10. But people were stuck at around 10 to the 5 to 10 to the 6. And what you can see is that if you make the devices bigger, the quality factors go up. So basically, as you change the amount of participation of your electromagnetic mode with surfaces and interfaces, then you can change how much loss you see. And there's this very nice parametrization and scaling. This from Chen Wang's work several years ago. The other kind of curiosity in superconducting qubits is that the losses get a lot worse at low temperature and low power. which is very weird, right? Usually, if I give you a material and I say, how lossy is this material? It's just like Beer's law, right? You just know I have this path length and then I have some linear absorption. But what this is saying is that if I give you that material and you cranked up the temperature, then you could saturate some of those losses. Or if I put in more photons, then I have less loss than you started with. This is now a plot of loss tangent as a function of temperature. And you can see that the loss tangent goes up with decreasing temperature. So that's bad, that's more lossy. And then similarly, as I crank up the number of microwave photons I put in a superconducting resonator, the loss tangent also goes down. So there's something that I'm saturating. So the general word for this that people like to describe is that these are two-level systems. You have something that can saturate. So if I drive it really hard or thermally saturate it, then I don't see as much loss. So there's a number of candidates for these two-level systems and general loss, mechanisms for loss and noise. You can have, there's an amorphous oxide in the Josephson junction and all over this device. You can have quasi-particle tunneling through your junction. You can just have classical linear dissipation at all of your interfaces. And then you can imagine surface spins playing a role in things like flux noise. So we basically started talking about this problem with Andrew Houck's group and Bob Kava, who's a solid state chemist, a few years ago. And we just took a hard look at this material system that Andrew was working on, which is very similar to what the IBM processors are built on. So it's an aluminum oxide Josephson junction, and then the rest of the device is made out of niobium. And we basically have two basic hypotheses for where this dielectric loss could come from. The first is just really dumb substrate contaminants, right? It's that if you don't do a good job of cleaning, then there's all this stuff that's there, and then that could lead to loss. The other possibility is that what Bob pointed out is that he had spent a lot of the 80s and 90s studying the oxides of niobium, and he said it's just a big mess. Niobium oxides are super complicated. You get every single type of stoichiometry. And he thought maybe we could see resistive loss from this because maybe you have a bunch of like weird superconducting phases and things like that. Okay, so there are sort of, two lines of attack. The first was just, let's just make these surfaces, clean and smooth and contamination free. We worked a lot on sapphire substrate preparation. And then the second line of attack was, let's replace this niobium with something else that has a better looking oxide. So if you just go one down on the periodic table, tantalum, which is a refractory metal, is known to have a very nice behaved oxide, which means that you always get it's a kinetically limited oxide where you always get 2 to 3 nanometers almost no matter what you do, similar to aluminum. And you always get the same stoichiometry. It's always Ta205. And the interesting thing is that this is really robust to processing and differences in microstructure. You just sort of always get this 2 nanometer thick layer. And we can even compare these things directly by doing things like variable photon XPS to build up a depth profile. This was some nice work that was done by Andrew's group in collaboration with some folks at Brookhaven National Lab, where they could see that in niobium, depending on exactly how you prepared it, you got all these crazy oxides that penetrated very deep into the interface, and it was just a big mess. Whereas in tantalum, everything is really sharply confined to this little 0.5 nanometer thick layer, and you really mostly get Ta205. So the punchline is that by replacing niobium with tantalum and being careful about our fab and contamination, we were able to break through this 10-year-long stagnation in superconducting qubit coherence and get devices that are robustly a T1 exceeding 300 microseconds. So it was around a factor of 3 improvement over the state of the art. And let me just emphasize here that state of the art was at like industrial fabs where you have a lot of control over the processing. Academic labs were not making 100 microsecond qubits by and large. They were making 10 to 20 microsecond qubits. So in some ways, this is an order of magnitude improvement over what you could normally do in your little academic clean room. And this is very robust. Like we have not made a qubit with under 200 microseconds, basically with this material system. Okay, so that was the story last year. And since then, what we've been working on are very systematic studies of sort of the remaining sources of loss. We're basically making these tantalum resonators, and this is work led by Avik Dutta in my group and in collaboration with a couple of graduate students in Andrew Houck's lab, Alex Place and Nathan Crawley. And the idea here is that we sort of isolate out one material system, we can move much faster and have access to a larger temperature and power range. So in these tantalum resonators, we're able to see evidence of this two-level system loss. So you increase the power and the quality factor goes up, which means that you're saturating some loss. And then, so this is something that I think is not generally done by the community. So this is very, very new data. But what we were able, what our approach to this was to say, well, we have some model for what our losses are. Let's just take that model seriously and take a full power and temperature dependence simultaneously, and then fit the entire data set. So this is now just power dependence curves at all of these different temperatures, and we scan over a very large temperature range. And then we can write down a model that we have losses that are associated with two-level systems, losses associated with equilibrium quasi-particles. That's this basically drop off here as you approach the critical temperature of the superconductor, and then something that sets a ceiling on all of this that's temperature and power independent. So with only like 6 free-fitting parameters, we can fit this entire data set very beautifully. And in doing so, the important thing here is that we can extract a parameter that appears to be robust and actually parametrizes the material losses. So now we have this kind of QTLS naught. We can do an independent measurement by looking at frequency shift of the resonator with temperature and get out the same parameter. And then we can compare whether or not we get the same parameter if we do these 2 separate measurements. And what you should look at is the red and the blue points, which are basically overlapping for all of these devices. Incidentally, yellow is what you get if you just do one of these power sweeps. So you overestimate the Q and it kind of gives you the wrong number. Okay, so the important thing is that with this parametrization, what we're able to do is look at the, for example, the surface participation dependence of all of these losses. So for example, here are a bunch of devices that are made with some procedure, and then here are a bunch of devices that are made with some acid etch, and you can see that the loss tangent is a little bit better after we do this acid etch. And this would be just impossible to tease out if you didn't do this full data fitting and parametrization. Okay, and this is just another graphical representation of this. You can just make a histogram of these apparent loss tangents and compare surface treatments. And we see that we do actually get this big improvement, about a factor of 2, when we do this final buffered oxide etch dip. Let me just skip this XPS story and tell you about, so then the other thing that we can do is look at, we have this ceiling that sets the top of all of these plots, and we can look at whether or not there's any surface participation dependence of that, and we see that it's basically flat. And we also use this as a way to diagnose a lot of what was ailing us in terms of packaging and coupling to sort of free space modes. So this parametrization is really powerful for being able to figure out whether or not you're measuring the right thing. And then we can compare to what happens when you make qubits, and we see that we're sort of generally lined up, but then we see this flat participation dependence. So there's something that looks like bulk loss that's creeping in for the largest devices. Okay, let me just skip the next story and say, the conclusion here, I would say we saw a really big leap in performance by, just trying a new superconductor. I'd say the whole field had done 3, maybe 4 materials, if I'm being generous, for a few decades. And we did a 5th one and managed to beat the record by a factor of 3. So I can write down like another 20 to 25 superconductors that you can absolutely deposit and fabricate, and are compatible with all of this other stuff. So we should clearly go try all of those things. So there's a grand project now. They're doing much more exploratory materials work. Our current devices are 2-level systems, but also bulk loss limited. So we're now kind of gearing up for a big project on figuring out what's going on with the substrate, trying different sapphire treatment and sapphire growth and things like that. And then I'll just mention that we have some ongoing work to try to do pump probe spectroscopy and spectral hole burning to try to understand the dynamics of some of these losses. All right, with that, I'll just acknowledge the group of people that worked on this. So the shallow and decenter story was mostly led by P. Sanctuason and Leela Rogers, and then the correlated sensing work is led by Jared Rafney. The chemistry work was done all in collaboration with Sue Nguyen and Rob Knowles in the chemistry department. The superconducting qubits work is done entirely in collaboration with Andrew Hauk and Bob Kava's groups, and was led by Avik, Russell, and then some of the materials work was Leela and Trisha in the early days of my group, and then Alex placed Kevin Crowley and a couple of really cracked undergrads, like just amazing undergrads, Huang Li and Yochi Gang, and Andrew's group. And there's a large number of funding agencies to thank. But let me just mention really quickly that it's a very exciting time for quantum at Princeton. There's a big quantum initiative. There's a lot of things afoot. There's quite a few faculty working in a diverse range of fields, and we have a postdoctoral fellowship for quantum where the applications are due in the fall. We also have this really nice undergrad research program, Coherent, where the deadlines are in January. So please take a look, and thank you for your attention.
Any other questions for Nathalie?
Could you comment on how to, or sort of how hard it is to sputter tantalum versus niobium?
Yeah, so there is a trick. If you just naively sputter tantalum, you get a different phase of tantalum from the bulk tantalum. So the bulk tantalum is a BCC crystal with a critical temperature of around 4 Kelvin. But if you just sputter and make a thin film, you tend to get the alpha phase, which is some tetragonal phase, and that has a TC of like half a Kelvin. So that's catastrophic because then you're dominated by equilibrium quasi-particle loss. But Dan Prober's lab figured out ways around this in the 90s. So if you just deposit at very high temperatures, then you can promote the alpha phase, or you can put in like a seed layer to promote the alpha phase. So it does sort of limit what you can do fabrication-wise. But yeah, so we deposited, I don't know, like 700 degrees or something, and then we get single crystal. Actually, we now get single crystal alpha phase tantalum.
Thanks. Curious if we can do it here at Stanford. Some level. Yeah.
Other questions? So I had a question about the TLS losses. I mean, if you can saturate them with power, can you sort of like pre-saturate them before you do your experiment?
Yes,
It's related to
yes.
Hilbert thing.
That is exactly what I'm working on right now.
Okay.
So actually, specifically, if you look at, so I didn't really talk about this curve very much, but so this part is just like partition functions, so that's obvious. But this part is weird, the fact that you get this really steep drop off. And it turns out that there are models that like Phil Anderson wrote down in the 60s that just account for this. So if you just have TLS interactions that determine your line width, then there's a 1/T dependence to their T2. So at very low temperatures, you get extremely long coherence times for the TLSs, and then that makes their saturation power very, very low. So this saturation power actually corresponds to something like you need a 40th of a microwave photon to saturate all the TLSs in the resonator, which is kind of amazing. So there's two things that are interesting about that. One is we should probably get another Dilfridge. Right, like really fighting for this base temperature. There's like a lot to win there. But the other is that maybe you can design your qubit gates so that you're intentionally driving your TLSs, right? Because now, and the most basic experiment that you can imagine is like let's say I do a T1. So I put population in my qubit, and then I wait some time, and then I measure the population. If in between the initialization and the measurement, I just put in a bunch of 2π pulses, those shouldn't do anything. But now, if there's a bunch of weird TLS dynamics that turn on with all of this microwave power, I should see this really long T1. So I think there's like a whole world of like, maybe the more general way to think about this, not to unify all of my research program too much, is that these are temporal correlations in the noise. Right. So like now, how do you design new gates that take advantage of these temporal correlations?
Awesome. Well, in the interest of time, we'll finish up. You're welcome to ask Nathalie more questions over the lunch. Let's thank Nathalie.